All right, well, welcome. This seems like quite a surprising jump in attendance. I guess it's likely because the first homework was due last week. But if not, if people are just watching the videos, I will probably then open up attendance to the 688 class now. If there's a reason why, is there a reason why people aren't here? Oh, it's a career fair today. Oh, okay. All right, we'll give it one more day then. Maybe people, that's such a good chance to miss the class then if you are at the career fair because it's all recorded. So, okay, good. Yeah, I'm glad that it wasn't quite this extreme a drop. I expect some people dropping, but you know, this is pretty extreme. Okay, so a couple quick announcements today. Homework 1 solutions. So homework 1 was due, I guess the last day you could technically use was Saturday if you use all 3 deadlines. So now submissions are closed. You can no longer submit. So hopefully everyone got them in. If not, if there's some problem, please email us right away because the first time we actually are okay understanding if people had trouble submitting or anything like that. But in the future, we probably won't be as understanding. The solutions will be out today. The solutions are going to be released on Piazza, and they're going to be released as images. So I take screenshots of the code and post those. And the reason I do this is for 2 reasons. First of all, it's a little harder to share. So I mean, you can still share it, but I don't like code to float there forever. We're probably going to reuse. What was that? No, it doesn't. And so in the following way. So the question was, does it make it easier to share? No, I don't think so. I guess there are more image sharing sites these days than text sharing sites. But it's really easy to email code around right when it's text, and you can just copy and paste code. And code finds its way. If you release text, I find it finds its way into people's solutions. So I just want to not do that. And the other reason I do it actually is that if you don't get the problem correct, and you want to check your answer with the code, you will have to go through the exercise of retyping the correct code. It is not that long. I think the XML parser, the whole thing was about 50 lines. So it's not that much code. But actually, I've always found personally it's a very good exercise to retype code if I really don't understand it, just verbatim. It really actually helps. It always helps me do this. If you feel differently, then you can use like OCR or something like that. Maybe you can figure out how to bypass the system. People certainly could. But the big thing is, please don't post this publicly. We're gonna teach this course in future years. Of course, this is the first time it's being taught, but we intend to teach it in future years. And we probably will reuse some of the old assignments, if not all of them. And we don't want the code to start being a thing where people sort of share this around. So please don't release the code. Retype it if you want to go to the answer, and if you feel it's a waste of time, then you don't have to retype it. We're also going to release histograms of homework scores, so you can look to see how you did relative to everyone else in the class. And the last thing was a couple people are asking us about partial credit on the assignments. And we're going to take somewhat of a hard line here. So in general, we won't give partial credit unless there's a really, really good reason for this above and beyond what the autograder gives. So we are modifying the autograders to give more partial credit automatically. But we're not going to give out partial credit based upon almost getting the solution right from the test cases, et cetera. And that's kind of for the sake of just ease. If we open those floodgates, then there's a lot of potential for partial credit. But also just because I think that at a certain point, it's not ideal. But whether your code produces the correct answer or not is ultimately what counts in a lot of cases. And so that's what's going to count here. If you almost get the right algorithm, that's good. You sort of have sort of gotten there, but you really need to get that the whole way and actually get the right answer. So for those 2 reasons, kind of ease of doing it and from kind of philosophical issues, this is why we're typically not going to give partial credit. There can be exceptions, as I said. If you really feel like you need this, then let us know. But in general, we won't. Homework 2 was released Wednesday, but I think you have to re-download it today. So I believe that one of the files for the first assignment was actually kind of incorrect the first time I released it. So re-download it today, please. And the autograders should all be out by now. It's going to be due not a week from Wednesday, but a week from Friday. We're giving 2 extra days on the assignment because it relates to topics we're going to learn about, at least the later questions, later topics we're going to learn about on Wednesday. We have to kind of do this because otherwise we would get stuck too much in the beginning lectures and have too many homeworks in the beginning. But we won't ever have a homework due on the same week we have lecture, but we can have it the week before. So it will. And when that happens, we'll try to push it back a few days just because I don't think it's quite fair otherwise. That means you'll have 3 late days starting from that Friday, so you could push it up until Monday in the latest, submitting midnight at Monday. And as noted on the website, some instructions and more information about the tutorial is going to be online today. OK, so let's jump right in and finish up from last time, talking about visualization. Are there any questions here first? Yeah. No, it should not be different. The code should be largely the same, actually, but you should re-download it, especially, in particular, only problem one. The problem one, the tweets file was wrong, so you have to re-download that. But the code and the problem itself is all the same. It's really just the data file that changed. So just re-download the package today, and then go from there. Oh, sorry, the question was, does the homework change a lot between our re-release one now and no? It was just the data file that changed. So just re-download so you can have the newest data file. All right, so let's jump now to finish up our talk about visualization. And in particular, we talked last time about visualization for one-dimensional and two-dimensional data, where our notion of dimension here was a little bit different from the normal definition, in that our definition of dimension really talked about independent dimensions, right? So if you have two columns where one's just sort of a label for the other one, we wouldn't really call that two dimensions. We would call that one dimension. But we talked when you have actually two-dimensional data, things like scatter plots or when one of your data is categorical, the other data is numerical, et cetera, we went through the categories of things you could use. In particular, we talked about, I can get a list here, but we talked about things like bar charts, pie charts, which you shouldn't use, histograms, scatter plots, line plots, box and whisker plots, and heat maps. Two different kinds of heat maps also, because people mean two things when they say heat maps sometimes. All right, so now let's talk about 3D data. And this is where things get actually very complicated. Because humans can we only have actually two dimensions to work with on a computer screen, right? So this makes it a very difficult task to visualize more than two dimensions. And so there are a wide variety of techniques you can use here, but ultimately these are all about trying to coerce a little bit more information so that we can maybe understand a little bit more than just two dimensions in the data itself. And that's kind of the point of visualizing higher dimensional data. So let me start by sort of actually driving that home with one plot, though. And I'll talk about one that you can do, which would be a reasonable initial way to talk about visualizing 3D data. Not higher than 3D, because humans can't even see in 4 dimensions, right? We can't even visualize that. So, but you might think that, well, we can see in 3 dimensions. So we may be able to create figures that are 3-dimensional. Right? And so the obvious analog would be, say, if you have 3-dimensional real value data, you could use something like a 3D scatter plot. Okay? And again, according to my sort of chart here, this should never be used for any type of data in any circumstance, no matter what the dimensions are. Because you can sort of see, right? If I show you this on a slide, you have no idea what that data actually looks like, right? It's showing you one projection slice of that data, essentially, and it's content-free. I mean, there's no way to see what's going on. So there may be some small cases where you can, mesh your surface correctly, which is kind of like just really doing a heat map. But in general, you don't want to do this, at least not for presentation of results, right? You should not think about trying to directly encode a 3D figure. Or directly sort of display or show in your paper a 3D figure. I'll talk about one exception to that in a second, but in general, don't do this. So this is just actually some data where I added another dimension to this scatter plot here. But as you can see, it is incredibly hard to tell what is actually happening here. The dimensions don't mean anything here. In fact, I actually have code that generates all this, which I didn't post last time. I meant to post last time, but it's now on the website. So you can go through all these examples. We'll go through them very briefly, because I don't want to spend too much time on it. But you can take a look at how we generate these figures. So the next thing I'll sort of bring up, though, is what's called a scatter plot matrix. So this is a way of viewing actually as high as you want to go dimensionality, in terms of dimensionality of your data. And I see these a lot in like tutorials on machine learning. And This is always the thing you're supposed to do first. And what this is this is a plot of, I see it being said to me to do it first. I'm not claiming you should do it first. In fact, I'll make the opposite statement in a second, but I do see this a lot. But anyway, what these figures are these take all pairs of dimensions of your underlying data, and they plot scatter plots of these things. Okay, so typically, for this to be sort of a real plot, you want to have all your dimensions being some numerical quantity. The same reason we want to restrict scatter plots to being numerical. You can have variations of this that will use something like box and whisker plots on some of them, and depending on whether they're categorical or real valued variables. But in general, think of this in the simple case as just all your variables are real valued. I have, in this case, 3 separate dimensions, but you could have more, certainly. And what I plot is I look at all possible pairs of 2 variables. So this one would, for example, be variable 1 and dimension 1 and dimension 2. And I'm plotting a scatter plot of those 2 variables against each other. And that's really all that these scatter plot matrices are. Now, on the diagonal, of course, that's not meaningful, right? Because that would be plotting a scatter plot of a variable against itself. They'd all just be diagonal plots without much information. And so instead, you plot a histogram, because that then gives you a sense of the distribution of the values there. And this is very common. It's sort of, there's a lot of code to do this very easily, and people seem to really like them. Now, I have to say, I don't really like these that much. Just this sort of personal taste. I find them very hard to interpret, right? Because you're sort of overwhelmed with data here. And the actual shape of this data is very hard for me to tease out from this plot like this, right? I actually can't, even knowing exactly how I made the data, it's hard for me to see how I made the data from this plot. So I tend to recommend not doing this, though you're welcome to, as long as you have to understand that you have to spend significant time actually interpreting these plots. They're not going to sort of jump out at you. And I would definitely not use them for presentation. So it's OK to use them for exploration if you want to. So if you want to sort of spend the time and figure out what each of these things is and sort of how they correlate, that's OK. I would not use this, definitely don't use this for presenting your results to someone. It's a question, yeah?
When you're trying to understand like 3D functions or something, like a plot like a surface of a function on a 3D scale.
Oh, OK.
Using, I mean, for that 3D visualization is sort of useful for yourself.
Yeah. So the question was about 3D visualization. And I'll actually come with an example of that in a second. So that's the one. The no there for this case is a no in terms of don't put that figure in a paper. Don't print it on 2 dimensions. Don't put it in a static display where you can't interact with it. That's a very bad idea. And oftentimes, if you do have a 3D function, it can be better to visualize it kind of as a heat map, where you would have actually 2D coordinates and then some like a color as the height level, which we'll talk about in a second, actually. But I would say I'll come to an exception, but in general, I'm talking here about presenting the data, and in a non-interactive way.
Is having multiple 2D charts better than having one 3D chart?
The question is having multiple 2D charts better than having one 3D chart? So this, I would say, if your hand is forced and you have to display one of these 2, then display the second one. It's much more interpretable. But don't display either if you can help it. At least not in terms of, again, this is OK for if you're willing to invest the time in understanding your data. So you kind of see, right, there's, the variable 1 versus variable 0 has this kind of pattern like this. Variable 2 versus variable 3, these are labeled by 0 indices here. It's a pattern like this, and they all have their own distribution. You can kind of get some intuition there, but it takes substantial time. And frankly, this is synthetic data, so I created it with some function, which I'm going to show you in a second. Your real data is never that nice, so it'll just be lots of kind of messes for the most part. And it takes substantial time to figure out really what's going on here. Now, the nice thing about this, though, is at least for 3 dimensions, we do have other possibilities than just those 2. So there are other ways to visualize 3 dimensions in a way that's actually somewhat intuitive. So I'm going to show 2 examples of that that are bubble plots and colored scatter plots. All right. So let's talk first about bubble plots. And then at the end of this, these are the last 2 examples I have. So then we'll jump to linear algebra next. So a bubble plot is a 3-dimensional plot But instead of trying to have a third axis that you represent kind of spatially, you represent the third axis in terms of the size of the dots. So here I have my same scatter plot as before, but I'm showing dimension 3 in terms of the size of those circles. And I would already claim that this is a much more intelligible representation than the other one, right? So you can kind of see, well, you see very nicely the first 2 dimensions in the scatter plot here, and you can kind of see that what's happening here is you're having larger values at the bottom and larger values at the top and smaller values in the middle, right? So I can kind of get a reasonable sense of what's happening here just from, a 2-dimensional plot, which this is the exact same data as this one, where I have no idea what's happening here, okay? So this is much nicer if you want to represent 3D data where you have all real values. Think about doing that. You can also, well, I'll show it next. The other possibility for showing a third axis while still having really a 2D chart is varying color. And now in this case, I'm actually showing a third dimension, which is a discrete quantity. So there's 2 classes here. And when we talk about classification, we'll see a lot of figures like this. These are actually 3-dimensional data where 2 of the values are real valued and 1 of the value is categorical, either class 1 or class 2. And what I'm doing here is I'm plotting 2 different scatter plots where class 1 is marked in blue and class 2 is marked in green. And this is actually very intuitive, I think, right? It's very obvious here. There are 3 dimensions here. I could show you this in theory as like a 3D plot where these dimensions are somehow separated by some number here, but that would be very unintelligible compared to this. This is kind of the standard visualization when you have 2 real valued categories and 1 discrete valued category. Okay, so these are just some examples. If you have a continuous third dimension, you can also vary that dimension in sort of grades of color as well. That's another thing you can do. But this hopefully gives you some idea of the ways to visualize these things. Now later on in class, we're going to talk about 2 things in a little bit more detail. We're going to talk about ways of visualizing high-dimensional data that go above and beyond this. We're really going to be talking there about things like if I have a large high-dimensional graph or a high-dimensional text document, how can I visualize that, right? Which is kind of a different, this is a very different category than this kind of stuff. This is really talking about, when I have a modest number of dimensions, how can I see what's going on? When you start having data with thousands of dimensions, these techniques, other than looking at very small slices, don't really work, right? Even a scatter matrix, which is the one thing here that had multiple potential dimensions, you do not want to view a 1,000 by 1,000 scatter matrix, so you really have to talk about some amount of dimensionality reduction in those cases. The second thing we're going to talk about is more about the presentation of data. So I've kind of been switching between your own exploring data for your own purpose and then doing it for someone else's purpose, right? For showing someone else. And we'll talk a little bit more about the presentation aspects later. Okay, so let me just finish up briefly now talking about libraries for plotting. And the one that you're going to be using in this class is called Matplotlib. Matplotlib is the standard plotting library for Python. It's not great in a lot of ways, but it has enough functionality that's become kind of the standard for everything. In particular, if you use the default options, it looks really ugly, so people don't really like how it looks. But it actually, in terms of functionality, is quite nice. It has a lot of functionality that makes it pretty easy, it's modestly easy, I'll say, to do this. So, the one thing I'll say is that Matplotlib is really aimed at generating static plots. So with a few exceptions, you typically don't use it to generate interactive plots. A lot of like the infographics you'll see are kind of the data graphics you'll see on websites are actually kind of interactive, and you can kind of interact with the data and click on certain lines and click on certain points and get some insight into what's going on there. And Matplotlib is not great for this. There are other extensions that are much better for this, so we may have time to talk about those when we talk about data presentation. But this is largely for static images or static images of plots. And because of the number 2 point, because they're so ugly, a lot of additional libraries have both been developed to Oh no, sorry, that was second point. So second point is that because they're so ugly, a lot of libraries have arisen to kind of make these look prettier, where you can actually use the exact same syntax, but you just have prettier looking plots. And also a number of additional libraries exist to have some sort of interaction in your plots. Okay, so we'll see how this goes. I had to type blind here, so we'll see. All right, so this is the notebook that's up on. Fortunately, this one's really easy because I don't have to do anything. I just press Control Enter the whole time, so or Shift Enter. So let's open up this notebook here. So can everyone? I don't even need it that big. Probably can be a little bit smaller. Everyone can read that okay? Okay, good. All right, so this notebook, and I'm going to go through it fast because it's all online, and really I would encourage you to just download it and go through it a little bit by bit. But I want to just highlight a couple of the things that we can do to plot all these plots. So all these plots were generated by this library here. And so in fact, all the plots you saw in my notebook were generated by the code right here. So you can regenerate them all if you want. Modulo randomness, because I didn't bother saving my random feed or anything like that. But let's just go through a little bit by bit. So the first thing is import all the matplotlib dependencies. It's a little bit actually funky, the kind of dance you have to go through to make matplotlib look reasonable in a notebook. I would recommend just copying all that code and putting it somewhere on on an easily accessible text file, then drop it in when you want to plot. Again, that's what I do. This sort of sets font. I don't know why, but the default font's tiny in most plots. They really want you to squint to find the font, so I make them bigger. The other thing I do is I use the Seaborn library, which is basically a way of making, it's a separate plotting library, but it also makes existing plots look nicer. So it also actually adds hooks to matplotlib that just make those plots look nicer when you use them. Okay, so I'm just going to go through it here and see how this goes. So import these things, import various numpy, etc. Draw some bar charts here. So this is the bar chart. So the command that's of importance here is called plot.bar, as you might imagine. Just as a little aside, what I'm doing here is I'm generating a random array where I have some number of dogs, some number of cats, and some number of rabbits, 10 dogs, 7 cats, and 3 rabbits, and then permuting them. And then I run this thing called collections.counter to count the number of items there are in that, distinct items there are in that array. And if you don't remember that, so this is how I did it. If you can't remember how to do stuff like that, use Google. It's really going to be your friend. Okay. Okay. So the important part here is the plot.bar function here. And then this just sort of sets things like the label. It gets rid of the X ticks from being here and here to move them over a little bit and label them with the labels dog, rabbit, and cat. And then it saves the figure as a PDF. Very important here. Please use the PDF extension when you save files. Do not use PNG extension, especially if you're going to put this in a document that you're going to share. It doesn't really matter if it's only on the screen, but if you ever save something to like a LaTeX document or a Word document, please save them as PDFs. Everyone that interacts with you afterwards will thank you for doing it. So please do that. I don't know why PNG became the standard to save files in, but just please use PDF. Okay, pie charts, plot.py, similar functions. I'm not going to go through the details here. I'm just going to show you the main functions you want to call. It gives you a nice, ugly pie chart. Because remember, Seaborn refuses to actually implement pie charts, so the nice graphics of Seaborn actually don't translate to pie charts. Those are off limits. Histograms. Plot.hist is the function. You should use that in your homework. So plot.hist does two things, actually. It returns both a set of arrays that describe where the bins are and how many are in each bin, as well as actually generates a figure that displays the histogram itself. So you can do this and see a nice histogram. Scatter plots, just plot.plot, but then normally plot.plot will make line charts. So instead, put the dot there, and that'll do separate dots for everything. Gives you a nice scatter plot of everything. Line plot is same thing, but you use lines instead of dots. Gives you a nice line plot there. Box and whisker. Actually, for some reason, Seaborn doesn't override plot has a plot.boxplot command. So plot is the matplotlib interface that you typically use. For some reason, Seaborn it overrides the other plots to make them look pretty, but does not override the box plot. So if you use Seaborn, use seaborn.boxplot. All the other commands are exactly the same as you would pass to plot.boxplot, but it looks a lot better. Looks very pretty. In fact, I can even show you what it looks like otherwise. It looks really ugly if I do this. All right, that's hideous. Also doesn't draw the little outliers anymore. It doesn't, so I don't know why, but do that. Then it'll look beautiful. People are relieved. I hear a sense of relief. All right, so now other things. I'm not going to do too much. So the heat map. Remember, I had two versions, like really a 2D histogram version, and the command for that is actually plot.hist2d. So when you talk about a heat map in terms of a 2D histogram, you actually want to use this hist2d function that generates this kind of thing. The other stuff I'm doing here really is just about setting like the right color map for it and things like that. The matrix version, I actually went through a lot of work here to get the matrix sort of outlined properly, but there isn't too much here. The main actual function here is imshow. So imshow plots a matrix as an image, and I just set up the matrix to have the proper numbers in it. You can go through the logic here to do that. That looks like this. Also, the labels take a little while to get in the right position and everything. A scatter matrix is actually, there's no good command in Seaborn on, well, there is, but the command in Seaborn, again, there's no good command in matplotlib to do this, but Seaborn has a very nice built-in command called pairplot. So you can run this pairplot command. It actually takes as input a data frame, a pandas data frame. So you actually set up your data in a pandas data frame, call seaborn.pairplot, and then that generates a nice looking margin. Well, there we go. It just takes a little time to do all that hard work of generating these plots. Bubble chart is actually plot.scatter, but then you set the s variable to be equal to some third dimension here. For some reason, like this, I have to set the color here, or the colors look ugly. It doesn't use the Seaborn colors otherwise. They're lovely little hacks like this. They don't quite match up always, so you can take this as kind of one example of a bunch of charts you can make, but chances are, if you want to do something a little different than this, you'll have to figure out how to make them look kind of nice. Color plots, again, just to show the last two. This is the different color plots. And then finally the last thing. So this is now actually finally a 3D plot. And one thing you noticed I did was at the very beginning, well, maybe you didn't notice that, but at the very beginning of this document, I had a command called percentage matplotlib inline. Without that command, matplotlib actually won't display the figures in your notebook itself. So it won't display them in the Jupyter notebook. So you issue that command to make them display it inline. There's also a function called pylab, which is sort of a general technique that imports a lot of other things too, including charts. But I tend to just use the matplotlib one so as to not kind of cloud my my space with too many variables. The last thing I'll say though is if you do want some small degree of interaction, we'll see how this works on the display here. I have no idea if it will or not. Instead of matplotlib inline, use this matplotlib notebook command. This gives you a hopefully, and it is not working on this. Okay, so yeah, I had a little bit of a worry that it wasn't going to work here. Now let's just try restarting and see if it works one more time. Okay. I have a feeling it's from displayed. So you can try this out on your own. I did it on my own computer before. So yeah, it's definitely not displaying on the third screen. Anyway, you can try it out on your own. And what this does is matplotlib notebook actually plots a somewhat interactive notebook. So if you have a 3D plot, you actually are able to interact with it to some degree here, and you can rotate the axes and kind of look at the data from different angles. And that's the one time where maybe a 3D plot's okay if you can interact with it and kind of visualize what's going on. Again, sorry, it doesn't work on the screen here, but it does work on the laptop. I love how displays work. I mean, I have no idea why that would be the case, but it seems to be the case. That would be the one time where I think it's kind of okay to use a 3D plot, is not for presentation, but for your own sake. If you want to visualize data and you can rotate the things as you go, then it's actually okay to visualize it that way. So okay, I realized that was very, very fast, and I intended to be kind of fast there. The main point of this is that the code to generate all these things is where I made all those figures is on the website now. You can download it, you can execute it in your own notebook, and hopefully that will give you some idea of how to make these plots. If you have other plots to make, Google is your friend when it comes to these things, because I would never remember how to type all those syntaxes without Google to help. So by all means, Google the docs or just Stack Overflow for help with the syntax of these things. Okay, so moving on now. I believe, okay, let's see where. All right, I may not do that again. I have one for NumPy as well, but I probably am going to not do that. Just because that's kind of a pain. You'll have to go through the notebook yourself. I'll try to see if I can get a better one where it actually mirrors me and I can actually do some live coding, but well, I have to look backwards all the time. It's probably not that efficient. All right, so let's start now with the next unit of this class, or the next lecture, really today's lecture, which is on matrices, vectors, and linear algebra. So I actually originally was going to talk about time series today too, but I think it didn't quite fit in the time I had. And hopefully I'll get through all this, at least the first three parts of this today. And then next time we'll move right on to graphs, but also talk about sparse matrices. So the outline of this lecture is really talking, actually, I always do this. I've just been talking this whole time there. Are there any questions about the visualization part? I always forget to stop and pause and ask that. But questions about visualization? Yes?
Kind of philosophical one, but can you briefly explain why PDF is the standard one, but PNG is lower than?
Okay, so why is PDF better than PNG? So PDF is a vector format, meaning that if you zoom in to your images, they will look good, whereas PNG is a bitmap format, meaning that they are just bitmap images. That's fine for displaying on your screen. For displaying in a paper is horrible. It will take up more space, and it will print really ugly. And if you try to zoom in, you won't be able to see anything. So just use PDFs. Not that PDF is a great format either. It has its own problems, but it's the standard vector format everyone has. It's probably what your papers are going to be written in if you use anything. But I mean, even if you copy it into Word, actually Word will generate a vector representation of a PDF if you do that. So I mean, all my figures here are PDFs. And let's see. So all these are PDFs. And if you see if I can do this, I don't know if it'll let me do it. Now, well, let me actually zoom in here. Let's see. And it's really starting to get kind of annoying. Okay, so if I drag this over here, I can actually zoom in to these things, and they look very nice, right? So they look very clean. Whereas if you and if PowerPoint lets you do it more, you could just keep zooming as much as you want, and they'd be very nice vector graphics that look beautiful at any scale. That's much nicer than PNGs. Okay, back to. They're also smaller. I've seen a lot of files that are megabytes and megabytes because Word embeds bitmaps very poorly, and so these files that for zero reason are huge. So just use PDFs. Okay, so we're going to talk today about matrices and vectors. And we're going to start out by defining what matrices and vectors are. I am going to use, throughout the rest of this class, I'm going to use vector notation a lot. In fact, I think in one of my previous faculty course reviews, one of the comments was that I spend too much time I like vector notation too much, that it got to an extreme case. So I really, and I am guilty of that. I hopefully won't do it. I'll try to cut down a little bit, but I really like vector notation because it actually makes things simpler, right? So oftentimes there are expressions that if you write it out term by term, these become very complex, lots of sums, lots of indices, things like this, that when you write it as a matrix or a vector, some sort of mathematical operation, it becomes very, very simple. So I use these a lot, and in the rest of the course, I will use these things a lot. And they're also a very nice way of representing data. So we're going to start by talking about sort of the basics of matrices and vectors, and then I'll talk about linear algebra. And actually, linear algebra is sort of one dimension of matrices and vectors, but there's other ones as well. So I'm going to sort of emphasize this, what I mean by that, in a second. So hopefully that'll make sense. Then we'll talk about libraries for matrices and vectors. This basically, in our case, will mean the NumPy library. That we'll also use for sparse matrices. We'll use the SciPy library, but for the most part, it'll be the NumPy library. So I went through our announcements already, and I want to now talk about other things. Let's see how much time I have here. OK, so let's talk about matrices and vectors. All right, so first bits of notation here. And I'm going to write this down here because I want to emphasize these things. And then when I write math, I like to write it down so it kind of sinks in a little bit. So a vector is the best way to think about it is a 1D array of values. Though, very importantly, there's a big difference in what I mean by array versus what I mean by vector. So an array is kind of a storage of how you store things in memory, right? That's what an array is. It's kind of a computational term, whereas a vector is a mathematical term. Now, I'm going to sadly kind of mix these a lot sometimes, especially when we talk about the NumPy library. It kind of intentionally mixes these a little bit, but know that I do mean different things when I say those things. So a vector is going to be a quantity that I'm going to write like this. This says that x is a vector with real valued elements, and that it has n of these. Okay? And the way I write this is I write it as a vector like this that contains each of those elements, where xi is the ith element in that vector. Okay? Now, by default, I'm going to consider a vector to mean a column vector. And this is actually an important distinction here, one that NumPy does not have. But I'm going to think of a vector as meaning a column vector. That is, it's going to be a matrix with one column and n rows. Okay? So that will become a lot more important shortly. But for now, just know that when I write a vector, I will always almost mean mathematically a column vector. Okay? If I want to have a row vector, that is a vector that looks like this. And these are different things again, right? If I want to have that, I'll write X transpose. And we'll talk about transpose in a second. Who here has had some linear algebra before? OK, everyone. That's perfect. So this is going to be all review. What I find odd, actually, is that the linear algebra we do here is all very, very simple. But yet, I feel like sometimes a lot of courses emphasize the wrong elements of linear algebra. Namely, they get very quickly into things like eigenvectors and decompositions without really focusing on kind of what the basics of matrix multiplication actually mean. And so hopefully we will, if you've taken linear algebra before, this is going to be easy, all of this. So trust me, it'll be extremely easy. But hopefully you still will get some insight into kind of what these things when you write things like matrix vector products. OK, so let's talk about next matrices. So a matrix is a 2D array of values. But again, there's a big difference between a 2D array, as it is represented computationally, and an actual matrix. So matrices are mathematical objects that actually have some operations you can perform on them, and they really have some meaning. But I'm going to use the following. I'm going to write A is an Rm by n to mean that A is a matrix with real valued entries, m rows, and n columns. Okay? And the individual so it's going to be laid out like this. The first element is going to be A11 up to A1n, M1, AMN. Right? Whereas here, as you can imagine, Aij refers to the entry in the ith row and the jth column. Similarly, this is a little less common, but I'm going to try to do this. I'm going to try to use the notation. So Aij would mean the ij entry. I'm going to try to use the notation Ai colon to talk about the ith row of the matrix. And Aj, so this would be the ith row. This is the ij entry. And then A colon j to mean the jth column. Okay. I admit I actually don't use those that much when I'm writing things, because what I'll usually do is I usually actually define a matrix in terms of its rows or columns, which are defined by some other symbol, like a vector. And so I'll actually define a matrix, where, for example, the ith column could just be a vector AI, and that would mean this column. That would be the next column, etc., up to n columns. So I will do that sometimes too, but I will try to be explicit about when I'm doing that. And if anything is ambiguous, please ask questions, because I may accidentally make it ambiguous sometimes, but I will try very hard not to. And now, after this definition, I want to kind of make the main point of this lecture. And that is that matrices and vectors, they're really doing two things at the same time. And I think actually most of the confusion about matrices and vectors stems from mixing up these two things. So on the one hand, when we talk about matrices from a standpoint of a lot of data science, what's really happening is that matrices are kind of the most obvious way we have of representing tabular data, right? So if we have a big table where we have a bunch of real valued entries, well, it really makes a lot of sense to store that as a matrix. And along with that, there's really this notion of a matrix as really a 2D array. So there's also a storage sort of memory layout that goes along with that representation of this data. Okay? So that's kind of the first view of what matrices are in some sense. And that's oftentimes why you will see matrices being used at all in data science tasks. There's actually no notion of anything but that. They're just a way of laying out sort of data in really a 2D array. But the second use of matrices, which is equally important, is matrices are also the foundation of linear algebra. And linear algebra is about manipulating and operating on systems of multivariate linear equations. Okay? So if you wonder, if I have this matrix operation of matrix multiplication, why is it defined the way it's defined, right? It seems like a very odd thing the first time you see it. Well, that definition really comes from this notion of linear algebra as a way of operating on linear expressions, whereas if you just think about the first one, there's no real need for matrix multiplication to be defined that way. I haven't defined it yet, by the way, but I will in a few slides. So it's important to understand those two views, that these things really both mean, from a computational standpoint, they both mean a way of interacting with tabular data, real valued tabular data, and storing real valued tabular data in memory. And they also mean a way of operating on and manipulating linear equations. So I'm going to keep hammering that home because I think it's important. And in particular, I think actually NumPy, for all the faults it has, actually does a pretty good job of separating these two things, where the first one is really the array view of data, and the second one are matrix operations. Not the matrix class. I would recommend initially, if you've heard of it, you don't use the matrix class in NumPy, but there's a set of routines that really apply to these things as matrices. And NumPy does a really nice way of kind of separating those two. So we'll see that in a second when we talk about NumPy. So let's take the first interpretation first, right? This is sort of, what do we mean when I say that matrices are a good way of representing tabular data? Well, if I have data like this, remember our old grades sheet, right? Our grade sheet, we started with a person ID, and then we had a homework 1 grade and a homework 2 grade. And here, person ID is really not a numerical value. It's just an identifier for the rows. So when you think about representing this as a matrix, you actually wouldn't really include that number in the representation because it doesn't have the same meaning as everything else. The matrix you would set up that actually represented this would be a matrix just of scores, where you would then have some separate index or lookup to indicate that the first row corresponds to person ID 5, the next one's person ID 6, etc. And the first column corresponds to the homework 1 grade, the second column corresponds to the homework 2 grade. Right? But this is really a notion of matrices as just a way of taking our data and kind of dropping it into some sort of storage form. And in fact, in this form, there's no real need for these things to even be real numbers, right? So it turns out that NumPy can actually represent any object, any Python object in a matrix. Now, that isn't very useful kind of mathematically. You can't really talk about, inverting elements where your matrix is a string. Some elements are a string. But from a storage standpoint, it makes perfect sense. Each of these things is sort of would be, in that case, kind of a pointer to some string. And that would make perfect sense as kind of an organizational way. So I think I mentioned before, for instance, pandas. Man, I'm stepping on this, or not stepping on it, but leaning against this table here. Pandas uses matrices as its underlying representation to store its data. Now, pandas is not just doing matrix operations. It's actually doing a lot of other things as well. But the matrix is actually a pretty nice way of representing those things, kind of computationally. The first view of the matrix, that is. When it comes to this first view, there's also a very important distinction, which, again, mathematically has no real meaning here, but from a practical standpoint of what matrices are and how they're laid out in memory, has huge consequences, and that is row versus column ordering. So it's very simple here, actually, the question. The question is, if I have a matrix like that, how do I lay it out in memory? Right? Do I do it by rows, or do I do it by columns? So in other words, do I lay it out by 100, 80, 60, 80, 100, 100? In other words, sequential in each row, or do I do it sequential in the column first? 100, 60, 100, 80, 80, 100. Who thinks it should be the first one? The row should be row-based. There's no right answer here. You can answer whatever you want, but everyone should answer. OK, who thinks it should be column-based? OK, excellent. The second group is right, so that's the right answer. No, it's actually very interesting. So these go by different names. The first one goes by C indexing. So C, if you create a 2D array, will actually, by default, order it by row. And Fortran, if anyone has ever heard of Fortran, we'll actually index it by column. We'll sort it by column. Now, the tricky part is, and there are some good reasons for this, actually, even though it sounds odd, maybe do it by column. By row seems more intuitive, kind of how we think about memory being laid out, just because we read that way. But by column actually has some advantages, namely the fact that we think of, for instance, 1D vectors as being column vectors. And so it might be more natural to think of this thing being arranged as vectors by columns than by rows. So the real reason, though, is that historically, for whatever reason, when people developed a bunch of numerical routines, they all wrote them in Fortran. And so every numerical routine you will find will assume, every sort of scientific numerical linear algebra routine you find will assume that matrices are ordered in column major ordering. Virtually all of them. And so if you actually use row major ordering, you have to tell it explicitly and think of this matrix as being transposed, essentially, is what you're telling it. But for the most part, they will always think of it as being column ordered. So if you want to use some fancy numerical routine, you're going to have to column order it anyway. Yeah?
The array in C, like an array per array.
Yeah.
Doesn't that create one array that has pointers to other arrays? And then the pointers are, since you treat the first one as row, the second one as column number, doesn't it?
Right. So the question was, when you think about C arrays, isn't the first one, the first index, really a pointer to another array, which is the index? Yeah. So the answer actually is no. If you have static sized arrays, they will actually assume it's laid out sequentially. Now, you can't actually do that always. And so if you, oftentimes in practice, yes, you're right, that's how it will be laid out. But if you actually have fixed size, they often will store it sequentially by row first. Because what happens is the first one points to, well, I don't want to get too into this, but we can chat afterwards. But actually, C will think of the second term as varying. The whole first row will be stored somewhere in memory. And so you will actually sort of hop through that, and when set up correctly, it'll actually be sequential. And the first row happens first, second row happens next, etc. So that's how it typically works. The question was, aren't they usually dynamic? Yes, but actually, if you make them in the right way dynamically, they'll still be ordered in this way with C ordering. I mean, you have to do it in the right way, but they will be ordered this way. Yeah.
So in the previous slide, you mentioned that you don't need to IDs in the matrix.
Yeah.
So what if the IDs are like non-uniform, some random series? How do we like organize that?
Yeah. So this is actually a great question. So the question was, if I don't need to include these IDs, what does that even mean? So if they aren't sequential or something like that. Yeah, that's actually a great question. So in matrix land, we index rows and columns by integers, or by either one. Actually, in math land, you use 1 base integers, and in NumPy, we're going to use 0 base integers. So actually, you have to get used to that as well. But when you think about it, row 0 doesn't really mean anything, right? It just happens to mean that it's the first row in this matrix, or row 1 mathematically, right? It doesn't really mean anything. The same way that if you use like a random hash of the person's name as their ID, it wouldn't really mean anything. It would just be an ID. And so the row index takes the same kind of role as some sort of label of that row. And in some sense, what we can view libraries like Pandas as doing is Pandas is just providing kind of a matrix where you can also label rows and columns. So there's no real reason why you pick 0 as an index. But what you would need then is you would need some other key that would map these IDs in the matrix or in the relational database sense to what index they actually appear on. And that's actually not that dissimilar from the database itself, where you map IDs, an index in a database where you map IDs to positions in the file. You would similarly have some map between IDs and indexes into that matrix. Different meaning of index there. Now I mean like the number of the row or column. So row and column orderings. Now, the last thing I'll say about C arrays, etc., is that in some sense you're right in that they can be wherever they want in memory when you allocate them, if you allocate them the wrong way. But it is more common to think about C matrices as being arrays that are stacked sequentially in memory, and therefore you actually have column ordering. Yeah, row by row. Yeah. Okay, the last thing I'll talk about is higher dimensional matrices. So from a data storage standpoint, a vector, right, is a 1D array, and a matrix is a 2D array. So why do we have to stop there? Why can't we have 3D arrays or ND arrays? And you actually can. They're actually very easy to specify from a computational standpoint. And these are called tensors. Okay, so the broad name for a vector or a matrix of higher dimension, or the analog of a vector or matrix of a higher dimension, is a tensor. You may have heard of this term recently. It's very popular these days as a cool sounding term, I think. It has led to a lot of its popularity. So again, when you talk about tensors, there is a very important differentiation between the storage of a higher dimensional array, which is very simple. Right? Higher dimensional arrays are very simple. You just have some extension of column or row ordering. You sort of, you lay out a bunch of matrices one after the other in some ordering, and that becomes the definition of a 3-dimensional array. And lay out a bunch of those in certain ordering, have a 4-dimensional array, etc. So from a standpoint of data access, it's very easy. You just keep adding new dimensions to index over. But from a standpoint of linear algebra, this actually becomes very, there start to be some very, very sort of tricky things that come up. And so not necessarily in what we're going to see today, but when you talk about even things like inverses, and certainly when you talk about things like eigenvalue decompositions, the analogs in tensor space are very, very complicated. So they don't sometimes always exist. There's sort of very odd properties here. And so the linear algebra definition of tensor is not a trivial thing. So tensors in the true mathematical sense are actually kind of nasty. As compared to tensors in the just pure memory layout space, which are very easy. They're just multidimensional arrays, and that's actually very simple to think about. So most of the tensors you hear people talking about are actually the first use of the term. So it's just basically convenient ways of laying out multidimensional arrays and data. So for example, the library TensorFlow really is not about tensors in the mathematical sense. It's about tensors in the sense of just storing really big multi-indexed arrays. Okay, so having sort of covered a couple of the issues as it relates to the first sense of the word of matrices and vectors, let me talk now about the second sense. This should be pretty brief because you've all taken linear algebra before, it seems like. So thankfully, it can be very kind of quick, this review here. But I want to highlight some of the main things of linear algebra. And so the first fundamental thing that we're talking about that I really want to kind of emphasize throughout the entire course here is that linear algebra is about linear systems of equations. So if I have a set of equations like this, so if I have some set of equations like 4x1 minus 5x2 equals negative 13, negative 2x1 plus 3x2 equals 9, that is a set of two linear equations with two unknowns, right? And you all know how to solve it. I mean, you solve it right by like, you multiply the second row by 2, you add it to the first row, that cancels out the x1 term, and you have a solution for x2, and you solve for x2, you plug that back into the other expression, and you get a solution for x1, right? You've sort of all done that in high school. And the nice thing about what linear algebra does is it lets us write those expressions much more compactly. So instead of writing this whole equation before, we just write it all as ax equals b, where a and b contain the coefficients of that set of linear equations there. And it's important that the reason why, for example, matrix multiplication is defined the way it is so that these definitions and that notation corresponds to the same thing as that equation there. All right, so let's talk now about some basic operations. Actually, I even had one. No, I didn't have one yet. Okay, so the basic operations we'll actually come across in linear algebra. The first one's addition. Ax, or a plus b. The ij element of this is just the ij element of A plus the ij element of B. Now, in order for, of course, that to be well defined, what this means is that in order to add two matrices, A and B have to be the same size. And same is true for subtraction, too. The transpose the transpose swaps rows and columns of the matrix. So A transpose, the ij element of that, equals A ji. Multiplication now. Multiplication is the one tricky one. It's not element-wise multiplication, but we've all seen it before too. So element-wise multiplication says, or sorry, matrix multiplication says that and now I'm going to write the sizes because they're very important here. So if I have a matrix A, which has m rows and n columns, and B, which has n rows and p columns, oops, B in. Then the product AB, the ij element of that is the sum over all k equals 1 to n of A I k B k j. And the way to kind of view this is that if you have your matrix A and your matrix B, then this equals some new matrix C. And the ij element here, so this is the one in I and j, is equal to, you take the ith row of A, the jth row of B, you take their corresponding entries, multiply them together, add them all up, and that becomes the ij element in matrix C, or in the product matrix. Now, I should have actually put a link to this. I actually have If this is not familiar to you, which I think it was for pretty much everything, if it's not, I actually have some online videos about linear algebra that may be helpful. We'll post a link to that on the course webpage. But you will have to get somewhat familiar with these operations, just really these ones, and then one more. Hopefully isn't too onerous, but we're going to use this a lot. So do get familiar with these things. Okay, so multiplication in particular, it is, I can just sort of read it here. It is associative, so it doesn't matter which order you do these things in. It is distributive, so if I have A times B plus C, or rather, sorry, associative means that if I multiply B and C together first, then multiply A, that's the same as if I multiply A and B and then multiply by C. Distributive means if I have some sum here, I can distribute it out. I can distribute the product over those two elements. And commutative, which it is not, means that AB does not equal BA. So you, unlike scalars, for example, you cannot flip the order of multiplication for matrices. In fact, it's really important to know what's going on here in terms of the size of these things. So you can only multiply two matrices together when the number of columns in the first matrix equals the number of rows in the second matrix, right? And the size of the resulting matrix actually is the number of rows in the first one and the number of columns in the second one. And that actually falls out very nicely from this definition here. This inner dimension here has to be the same, or this sum doesn't make any sense. So if I have a matrix product, it's likely, or not likely, by some definition of likely, I guess, that this alternative, the swapped product, doesn't even make sense syntactically because they no longer have the same number of rows and columns, or columns and rows in the two matrices. But even when they do, like say these are all square matrices, this still would not hold. It holds only for an extremely small class of matrices, and you can never assume it will. It basically never really holds in practice. So don't ever write that. Don't ever simplify doing that. Okay, so a few more definitions here. I think this will be pretty much it. Now talking about a matrix inverse. Yes, question.
Yeah, well, the previous one is also kind of general question, but still. So when you think about the multiplication of matrices,
Yep.
what do you think about the separation?
So there,
Did you put
yeah.
something about it?
Yeah, so there are actually 4 different ways to view matrix multiplications. You can view it as a bunch of inner products of the different rows and columns. You can view it as a linear combination of rows or linear combination of columns of one matrix, or you can view it as a sum of outer products of different rows and columns of different matrix. So I actually, I won't say which I think right now because it's actually important to understand all of those different views, as well as like the operator view, right? That's also an important one kind of mathematically. But for now, all I'll say is that if you want to have more insight into that, I have some text documents or some documentation, not documentation, some sort of brief tutorial material on it, and I would encourage you to look at that. So that's all I'll say for now. Okay, so a matrix inverse, there's the identity matrix, which is denoted I, which is a matrix that has 1s in the diagonal and 0s everywhere else. It's the identity. Sometimes people will write this like as I subscript n to say how many rows and how many columns it is. I is always a square matrix. But I don't ever do that because it's always implied this what the size of I has to be by the matrices you multiply it or add it to. So I just use the notation I to denote the identity matrix. And this is the matrix where if you sort of plug this into your definition of matrix multiplication and take any matrix A, what you'll find that I times A equals A. This also equals A times I, where importantly, these two I's are different sizes, right? Because the first one, if A is M by N, this has to be an M by M identity, whereas this one would be an N by N identity. So they are different matrices there, but I just write it like that, and that's the property of the identity matrix. The matrix inverse is for a square matrix. So importantly, you just probably can't see from over there, unfortunately. I don't really want to erase these yet. Well, it's all there. I just prefer to write this again. The inverse. If you have a square matrix, oops. then its inverse is the matrix such that when you multiply it A by its inverse, it equals the identity. And that works both ways. In this case, it actually does commute. And you can multiply it on the left or on the right, and it still equals the identity. Now, this is really extremely useful, specifically because it lets us do things like write solutions to linear systems very efficiently. So remember, I said that we wrote that big set of linear equations. Well, not big, it was very small there, but it could be very big, as ax equals b. So if I have some equations, ax equals b, then what I can do is I can multiply both sides by the inverse, right? So a inverse equals a inverse b. This then cancels out because this is the identity, and the identity times x is just x. So this implies that x equals a inverse b. This is all really simple stuff, but yet it's worth, I think, going through. This is all linear algebra we're going to use in this course. Now, that does not actually have to exist, the inverse, but we won't worry about that too much yet. We'll talk about it a little bit later, but just know that depending on properties like independence of the rows and columns, can you represent any one row by any other rows or any sum of other rows, then there actually does not have to be an inverse or an inverse to a matrix. A few last properties here before I move on to some code. When you have a transpose of a matrix product, U is equal to the two matrices transpose times each other. The same kind of thing happens for the inverse, but very importantly, that only holds the inverse of A times B. It's only equal to B inverse times A inverse if A inverse and B inverse are both invertible. They have to be both square and invertible for that to actually hold. So a lot of times we'll see some two rectangular matrices multiplied together where each one of those, where the product is square, because the product can be square, but they are not, they are each themselves not square, and people still write that, and that is wrong. It does not compute syntactically because non-square matrices do not have inverses. One special case of a matrix multiplication, which you'll see a lot, and I'll sort of use this notation a lot, is a inner product, it's called. So if I have two vectors, x and y, then x transpose is a row vector and y is a column vector, so that their product is actually a single scalar value, and it's just equal to the sum of all the product of all the corresponding entries there. So I'm going to use that notation a lot. You may also see like brackets sometimes. People sometimes define that as like x as this, but I'm going to use this, x transpose y. And finally, I may write this little norm here sometimes too. The vector norm is also called the Euclidean norm, which is equal to the square root of the inner product of the vector and itself. All right, so let's now briefly mention, I can't even get through this fully, but oh well. I'll use some of the code from next time. It's actually I'll get through most of it actually. All right, so now let's talk about software for linear algebra. So one thing that I want to emphasize here is that these things seem incredibly simple, right? What could be simpler than a matrix multiply operation, right? There's one algorithm for it. You know exactly what it is. I wrote it right there. You know, how many possible ways could there be of doing that? And the upshot that I want to emphasize here is that there are a lot of ways of doing it. And do not try to write these yourself. So, for example, take a matrix multiply. This is some C code, and don't worry, if you haven't seen C, we aren't going to use C at all in this course. But this is some C code that will compute a matrix vector. Oops, I wrote A there. I had a typo in my C code already. I didn't actually test this. I just wrote it. This should be a C here. I'll fix that later. But this code, if it did not have a typo here, would multiply A and B together. And if you compile this and run it, depending on your actual compiler, it'll probably be about 10 to maybe 50 or 100 times slower than an actual linear algebra library for doing this. And the reason is that there have been such intense optimizations of linear algebra code to work with things like the cache sizes and the vector units in your CPU that you cannot write anything that comes close to the speed of these specialized libraries. Don't try, just use these libraries. And in particular, you should make sure that your version of NumPy is also using one of these libraries, which I'll show you how to do in a second, because you don't want to be using this implementation of matrix multiply in your code. It will be much, much slower than anything else you could do. OK, so let's talk about NumPy then. So in Python, the library we are going to use to do linear algebra, both actually, I should say, we're going to use them to represent matrices and vectors as arrays, and we're going to use them to do linear algebra. It's called NumPy. And NumPy, it has some odd syntax, but once you get used to it, it's actually quite easy to use. And it is definitely the standard for Python. It's a little bit more verbose than other languages like MATLAB, but I think it makes up for it. Python more than makes up for the overall niceties of the language to put up with a little bit of annoyances when it comes to syntax here. Importantly, though, NumPy arrays. So the NumPy array object you'll work with is called an ND array for n-dimensional array, and that really should be thought of as an array, as a layout of values in memory, and not necessarily as natively a vector or a matrix. This is sort of actually very important. They were talking here, NumPy, the base unit is an array, not a matrix. There are some functions that provide the equivalent of matrix operations, but the default operators are really about arrays, not about matrices.
About matrices as a bunch of column vectors?
The question was, should you think about matrices as being a bunch of column vectors here? And yes, though in NumPy, they actually are row ordered. So you think about a bunch of row vectors in this case. But there's even more to it than that, which makes it kind of tricky. So for example, a 1D array in NumPy is neither a row vector or a column vector. There's no definition. There's no notion of row vector or column vector. It's just a 1D array in NumPy. So the way you get you imbue it with the notion of a column vector or a row vector is only through the matrix functions that it has. So this will take a little while to get used to, but once you do, it's pretty nice. The last thing I'll say before jumping into some code here is, and I'll probably get through like half the code in the end, is that I mentioned these specialized libraries for linear algebra. So these go by the name of BLAST and LAPACK. Actually, BLAST and LAPACK are just the interfaces for these things, so that they define a set of operations that any linear algebra library should go ahead and provide. And then there are highly optimized versions of the BLAST and LAPACK libraries. So the most popular ones are called Atlas OpenBLAST, which used to be called GoToBLAST. Not GoToBLAST, but it was actually a person's name, Goto. I think that's how you pronounce it. I'm not quite sure, actually. And Intel's MKL, I think it's called, stands for the Math Kernel Library. But what these are is these are very highly optimized, cache and vector unit optimized versions of certain operations on matrices and vectors that are, as I said, on the order of at least 10 times more efficient for some of the bigger operations than the version you would write yourself. If you want to see if you're using one of the fancy ones, call this call in NumPy. And NumPy __config __.show. That will tell you if you see a string like OpenBLAST or MKL or Atlas, it means you're good. If you don't, it means you're operating way slower than you should be. For the most part, Anaconda will actually provide you good versions of this by default, but you want to make sure of that. All right, so let's just do one example of these things then, of creating 1D and 2D arrays in NumPy. So I also have the code for this on the website. You can take a look at the code for on the website. And you construct, in general, matrices, 1D and 2D arrays. I'm going to do this a lot in NumPy with the .array call. And you pass it a list or a list of lists. And that will construct an array 1D array, 2D array, or higher dimensional arrays too. There are also some convenience functions you can use. So I can also use things like the .1s, the .0s, the .random, .randend function. And you can do the same for matrix forms. So you can also have a 2D array forms. So you can also specify 2D arrays of 1s, 0s, or random entries. Two kind of nice convenience functions here are the I function that generates the identity. Again, the identity is more of a matrix concept. This will generate a 2D array which corresponds to the identity matrix. And similarly, the diag function will generate a 2D array that corresponds to a 2D diagonal matrix. And we'll talk about this a little bit more. The best way to get familiar with these things is just by doing them. So this gets a little bit tricky when you start talking about multiplication of matrices versus multiplication of arrays, which we'll go through in some detail next time. But hopefully, you'll kind of figure this all out as you go, because it's best done by actually playing with the code. So I would encourage you to go through the rest of these slides here. I will cover them next class too, but then also look to see the code I posted, go through that, and start to see if it makes some sense to you. Okay, talk to everyone soon.